Hi there, this is Anastasio G. Pantaleon Jr. here and welcome to my YouTube channel. In this video, we will be discussing the basic ideal Rankine cycle. There are four processes in this introduction, so sit down and enjoy learning. There are four processes here and four parts also. We have here the condenser. So we have the R, we have the pump, the boiler. Okay. So what goes out from the boiler is a high pressure and a high temperature steam. We designate that as 1 and let that be designated as a pressure 1, high pressure, the highest pressure, and a temperature T1. We have the highest temperature. And if we look at that, here we have the point 1. This is where, okay, sorry for that. This is where your 1, the highest temperature, and this one is your pressure, pressure 1. Okay, just erase that. Pressure 1, the highest pressure. So, as the steam enters the turbine, it goes an isentropic process. And this is your TS diagram. This is your entropy line. And this is your temperature line here. So as it goes in isentropic process, this goes at a constant entropy. Okay. That means if we point that here as point 2 at a pressure 2, we have the pressure 2 here from your TS diagram. It goes by saying that using isentropic S1, meaning entropy 1 is equal to entropy 2. So if we put that graph here, we have S1 is just equal to your S2. But the pressure is now at a different point. We see this at point 2. And in your illustration, we see that it goes inside or within the boundary of the saturated line, wherein there are parts of it are vapor and parts of it are liquid. So in your TS diagram, this is the biggest part. This one is your part of vapor, and this one here, a little difference of that, if we exaggerate it, we go closer to that, we see your liquid. Now the main purpose, okay, of your turbine is to produce work. Here, okay, this line here, and it produces work. Turbine. And as it goes from the high pressure to the lowest pressure, we see this enthalpy line. There are differences of that H. This is your H1 and your H2. Now the main point is we have to find the value of your H2. So how to find the value of your H2? Okay. The main assumption is that we have, say, at point 1, P1 and P1. This comes also when you compute that, you will find your S1 and your H1. If it is at superheated value or superheated steam, okay, you either interpolate or find the value. using the CAT3 or computer-aided thermodynamic tables 3. Now at point 2, we have your assumption that P2 is different, but your S1, your S2, is equals to S1. And of course, okay, you can find that if you found it to fit that it is within the saturated line. How do you gauge that? Is you have to find the SG. Okay, SG, this one here, this is your part SG. SG at pressure 2 should be greater than your S2, which is also equal to your S1. So there you can find that it is saturated. But if your SG is lesser than your S2, which is equals to your S1, that means you have to find the value of your S2 in the superheated region. Okay? Heated. And you have to interpolate. But if you find your SG greater than S2, which is equals to your S1, and you found it saturated, okay, you have to say S2, which is equals to your S1, is equals to SF at pressure 2 plus X2 SFG at pressure 2. And then you can derive your X2. Therefore, your H2 is equal to HF at pressure 2 plus X2 multiplied by HFG at pressure 2. Okay? So you can find the work by H1 minus H2. Okay? In the part of the condenser, we have it is assumed that it is releasing heat at a constant pressure. This is your QR or heat rejected from the system. So the condenser will try to make the liquid as much as possible at a saturated liquid line. So what goes here must have saturated liquid at pressure 2. What you mean by that is it should not go beyond the saturated liquid line and goes to subcold, or else you will have to risk uh, the inefficiency of applying more heat in order okay, to gain momentum, so on in your boiler. We will be discussing about that. So heat rejected means QR is just equal to H2 minus H3. But what is H3? So at point 3, we have a saturated, okay, at pressure 2, but also H3 is equal to F at pressure 2. And we need to find also the specific volume. We have V3 is equals to Vf at pressure 2. Okay? We will use this specific volume to find the work of the pump. The work of the pump is almost the same as isentropic, but we will assume this, and it is very evident that the liquid is incompressible, so we have at a constant volume. So we have an isovolumic. Okay, here isentropic, here isobaric, and the work of the pump must be isovolumetric. So we have your 3 here and we have your 4. So we have your 3 and we have your 4. The same volume, V3. V4 is equals to your V3. So the work of the pump is therefore equal to H4 minus H3. But it's also equal to your V3, which is also equal to your V4. Of course, we have an isovolumetric process here, and we will multiply that with pressure 1 or pressure 4, but the pressure 4 is the same at pressure 1. This is your constant pressure, okay? Pressure line, this one here. So pressure 4 is just equal to your pressure 1. So pressure 4 equal to your pressure 1 minus P3, which is also equal to your P2. Those, you find the work of the pump. How do you find the H4? Of course, it is equated in that. We have H4 is equals to H3 plus work of the pump. Okay. Finally, okay, first we have to first signal as the working the pump. And finally, we have the heat addition. Q addition is just equal to your H1 minus H4. Okay. H1 minus H4. But we all know this is your 0.4. The pressure of 0.4 is equal to your pressure 1. Okay. The H4 is given from here. Okay. So therefore, all of this is given. H1, which has been stated in your initial calculations, and you have your H4, which is at the later part of the fourth stage or stage 4. Therefore, the work net is equal to the work turbine minus work pump. And you have also to find the thermal efficiency of the cycle. Thermal efficiency. So thermal efficiency is just equals to the work net over the heat addition A, which is equals to H1 minus H4. So that is the ideal Rankine cycle. I hope you enjoy learning. Thank you and have a good day.